we need to come up with a formula for the confidence interval for population proportion. Like for population mean, the confidence interval is going to be based on a sample statistic. In this case, it'll be P prime, the sample proportion, and then we're going to add and subtract to it the margin of error. Now, the margin of error includes two things from for the population mean confidence interval. We either took a value from a t-distribution or a z-distribution, depending on what the distribution of x bar was, okay, given the assumptions that we could make. And then the other piece was the standard error of the mean, or the standard deviation of x bar. So we can think of that margin of error is going to be either a t or a z. And then we're also need the standard deviation of P prime, okay, to go into that margin of error. So, all right, so we got to determine what the distribution of P prime is. So let's talk a little bit more about P prime, this sample statistic. It's going to vary from sample to sample. So P prime is a random variable, just like x bar and s. And as such, it has a distribution. Okay, now it turns out when we have a really large sample size, all right, and then if we've got a theoretical probability, or that population probability P is not real close to either 0 or 1, it's somewhere in between, not close to either of those, P prime will follow an approximately normal distribution. Okay, so we have to make this assumption, large N, P not real close to 0 or 1, but then P prime has a normal distribution. So we can use Z, a Z value, in the confidence interval. So we can say that the random variable P prime is normal. Its mean is P, all right? The mean is going to be the population proportion that it's estimating. And the standard deviation is the square root of P times Q over N, where Q is equal to 1 minus P. Okay, so that gives us our standard deviation of P prime, so that gives us the other piece we need to come up with that margin of error. So the 100 times 1 minus alpha percent confidence interval for P, it's using the Z distribution. We take P prime, add and subtract the margin of error, which we determined is going to have a Z value, and it's going to be that Z value such that we have alpha over 2 in the tail, and then we multiply it by the standard deviation of P prime, which is P prime times Q prime over N. Since we don't have access to P or Q, those are what we're trying to estimate, we're going to use the sample proportion, all right, and then the 1 minus the sample proportion, right, where we remember that Q prime is 1 minus P prime. Okay, let's find a 95% confidence interval for population proportion given a sample size of 50 and P prime of 0.75. So we're filling in P prime plus or minus, we want a Z value, and because we got a confidence level of 95%, that means alpha is 0.05. So alpha over 2 is 0.025. And then that's multiplied by that standard deviation of P prime, so P prime, Q prime over N. So let's figure out Q prime is 1 minus P prime, so that's going to be a 0.25. And let's determine what this standard deviation is. I'm going to take 0.75 times 0.25 over N of 50. All right, so those are separate. And that is equal to 0.06, approximately. Okay, so plugging values in, we get 0.75 plus or minus. So when we looked at confidence intervals for sample mean or for population mean using the normal distribution, we found that the z-value for 95% confidence interval is going to be 1.96. So that's times that 0.06 that we calculated. So we get a lower bound of 0.632 and an upper bound of 0.868. Okay, so that just kind of gives us the mechanics of calculating the confidence interval. It's helpful to do the standard deviation piece first and then plug that into the confidence interval when you get there. So let's look at another example. A poll of 12,000 voters were asked in a poll what the most significant issue was in the upcoming election. 780 answered the economy. We are interested in the population proportion of voters who feel the economy is the most important and want a 90% confidence interval. Okay, let's first of all define this random variable p prime. So p prime is the percentage or proportion of the sample that feel the economy is most important. So now we can calculate the value of p prime because in this example it's not actually given to us. So we want to put the frequency that relates to what we're looking at, the characteristic that we're interested in on the top. So we're interested in those that think the economy is the most important. So that's 780 over the sample size of 1,200. Okay, so that gives us p prime, or the sample proportion. So we get 0.65, or 65%. Now we can use that to determine the distribution. So we're going to say that it's normal. We got to use that 0.65, all right, to estimate that distribution. And then the standard deviation, right, is we're going to take that 0.65, multiply it by 1 minus 0.65, which is 0.35, divide by n, which in this case is 1,200. Okay, well that is equal to approximately 0.014. Okay, so there we have the distribution of p prime. Now let's calculate the confidence interval. All right, so we're going to take our p prime, 0.65, plus or minus. Since this is a 90% confidence interval, we're going to use that z-value that goes with it, which is 1.645. All right, times that standard deviation that we found, 0.014. That will give us a lower bound of 0.627, upper bound of 0.673. Okay, and the margin of error is 0.023. Okay, now what would happen if we were to increase the level of confidence to 95%? All right, so a little bit of a refresher here. So when we increase our confidence, we have to give something up. So the confidence interval will be wider. We lose precision when we gain confidence. Okay, let's look at this next one. Quality manager of a fortune cookie company believes that a larger than acceptable proportion of paper fortunes being used are blank. Suppose she takes a sample of 320 fortune cookies from the production line and 45 of the paper fortunes are blank. Round to 2 decimals. Okay, so we want to define P prime. It is the proportion or percentage of the sample with blank fortunes. And if we want to calculate it, all right, we're going to take our total sample in the numerator, 320, and put the number that are blank, 45, in the numerator. And that gives us a P prime of 0.14. So that gives us P prime is normal, mean of 0.14. And to calculate that standard deviation, we take that 0.14, multiply it by 1 minus that, which is 0.86, divide by the sample size, and then take the square root. And that's going to, if we round to 2 decimal places, give us 0.02. 0.02. Okay, let's construct the 95% confidence interval. We start with P prime of 0.14, add and subtract. We want the appropriate z value. So to go with 95% confidence level, that's 1.96, and then times the standard deviation, which is 0.02. So that gives us a lower bound of 0.10, an upper bound of 0.18. And the margin of error is 0.04. So now we want to explain what this interval means. One way we could say that is we are 95% confident that the interval from 10% to 18% contains the true proportion of blank fortune cookies, or blank fortunes. So the key things there is we got to name our confidence level, and then we want to identify that that confidence is in the interval. Okay, so the confidence or the probability is placed in the interval because that's what's random and is based on a sample. So let's look at the next one. Suppose we want to lower the sampling error, which is another way we could talk about margin of error. And how do we accomplish that? All right, so hopefully you're thinking through those different ways, and one of them is to increase the sample size. That will reduce the margin of error, the sampling error. So increase n. And then there's one other way, which hopefully you're thinking through, and that is to decrease something, and that would be to decrease the confidence level. All right, if you haven't already practiced one on your own, go ahead and pause, practice this one, and then come back and take a look at how it's done. Okay, define the random variable p prime in words. So p prime is looking at the percentage of the sample that buckle up. Now, if we want to calculate that, Okay, in the numerator, we want the number that buckle up, so 320. In the denominator, we look at the sample size, which is 400. And that gives us a P prime of 0.8. So P prime is normal, mean of 0.8, and standard deviation of 0.8 times 0.2 over n, which is 400. Take the square root of that, and that it gives us 0.02. So now I look at our 99% confidence interval. We're going to take that 0.8, add or subtract. We want the right z value, so for 99% confidence level, that's 2.575. Multiply that by the standard deviation of 0.02. You get lower bound of 0.749 and upper bound of 0.852. And that's a margin of error of 0.052, so 5.2%. So if we want to give an interpretation of this, we can say that there's a 99% probability that this interval from 74.9% to 85.2% of drivers buckle up before driving their car.